All right, so what we're going to do is apply all of the derivative properties to a function here. And what you notice is I have a function on the left here, and I do have its graph to the right just for reference. That's one thing about, one nice thing about technology is that even though we have all this beautiful calculus we can do, we still have the technology to graph these functions. So what we can do, though, is answer questions about the graph. You know, what if you wanted this exact coordinate right here where the relative minimum is, or where this relative maximum is, or where is that point of inflection? So those are questions we can much more easily answer by using a little bit of calculus. So just to recall, we know that the first derivative tells us a lot about a function. It tells us whether or not a function is increasing or decreasing. Remember that it's increasing if the derivative is less than 0. I'm sorry, if it's greater than 0. Whoa, that was pretty good. Greater than 0, and it's decreasing if the derivative is less than 0, negative. And we know that if f prime is equal to 0, we call those critical numbers, meaning that something could be happening at those numbers, but we need to do a little bit of analysis to figure out what is going on at those numbers. And what that leads to is what could be happening there. That could be a relative min. It could be a relative max. Or it could be nothing. So again, the first derivative test is what's going to help iron that out for us. Now, another thing that was very helpful was the second derivative, and that answered more questions about concavity. If the second derivative was negative, that meant it was concave down. And if the second derivative is greater than 0, that meant concave up. And if f double prime is equal to 0, after some further analysis and after testing the concavity on both sides, it could be a point of inflection. But again, we never know for sure until we do the analysis. So that's where we're going to get into it here. Now here, this one looks like it doesn't have any tricks to it. It looks like there is a definite min, a definite max, and a definite point of inflection. In fact, remember that at the maximum, that kind of verifies that yes, the first derivative is equal to 0 there. And remember that the point of inflection is basically the point where the slope is at its steepest going in one direction. So that's the point where the slope starts changing back the other way. So these slopes are all pretty negative and they're all going into the positive direction. So here we're talking about the max slope in the positive direction, and then after that point the slopes turn around and go the other way. So without any further ado, let's take a look at our first derivative here. So f prime of x is equal to, power rule says that that's negative 3x squared plus 12x plus 36. Now we know that if we want anything interesting to happen, we know we want that to be equal to 0. It's never undefined, so we don't have to worry about any critical points coming from that. Now the easiest way to solve this is I'm going to factor out a negative 3, and I think I'm in trouble here. Negative x squared minus 4x. Oh, no, never mind, we're good. Minus 12 equals 0. Okay, for a minute I thought I wasn't going to factor, but it will. And then the easiest way is to factor. Now, of course, if you can't factor the quadratic, you can always use the quadratic formula and at least get approximate solutions. So we know that factors as x minus 6 times x plus 2. And that means right away that x is either 6 or negative 2, and those are my critical numbers. Now, again, keeping the graph in mind up there, it looks like that the max occurs at 6 and the min occurs at negative 2. But again, our analysis is going to tell us this. So the sine graph for f prime, so here's what it looks like. So we know we have a 0 at negative 2. We know we have a 0 at 6. So we plug in what we call test numbers. which are numbers that are on each part of the number line here. You notice that those two critical numbers divide the number line into 3 places. So I'm going to pick a test number here. I'm going to pick a test number here and here. I'm going to pick -3 because it's not too much different than -2. It's just below. I mean, we could pick -10 if we wanted to, but that might not be something you want to do. I have a golden opportunity to use 0 because that's going to tell me what's happening on the interval -2 to 6. And here I'm going to use 7 because that's going to tell me what's happening on the interval 6 to infinity. So we plug each of those numbers into the first derivative, and which version of the first derivative do we use? Well, I'm going to use the factored version for a reason. So I'm going to say that f prime of x is -3, x minus 6, x plus 2. And if I plug in -3, I get -3 times. Now -3 minus 6 is -9. -3 plus 2 is -1. I get a negative times a negative times a negative, which is a negative, and I really don't care about the number. But that tells me if my first derivative is negative, that means that I'm decreasing on the interval where the -3 is. So I'm going to write an arrow going down for decreasing. Well, plugging in 0 should be a piece of cake because 0 likes to wipe things out. So that's -3 times. Now 0 minus 6 is -6. 0 plus 2 is +2. And again, we don't really care about the number, but it is positive, so that means it is increasing. Now, right away, that tells us we do have a minimum at -2. And our graph told us that up there. In fact, if I just scroll up there, you notice the minimum is closer to 0 than the maximum is. So I'd say that's a good sign. So plugging in 7 now, we get -3 times. Well, 7 minus 6 is 1. 7 plus 2 is 9. And again, I don't care about the value, but I do care that it's negative. And just like that right there. So we can answer a lot of questions already. We can say that this function is increasing on the interval -2 to 6. Because remember, those were the endpoints of the interval. We're just using a number in the middle to test it. And it's decreasing on 2 intervals. Well, it's decreasing to the left of -2, so that means -infinity to -2. And as well, 6 to infinity. And remember, the proper use of interval notation would put a u in the middle of those, telling you that that is the entire set of values where the function is decreasing. Now also, there's a relative, well, let's see. At -2, it goes from decreasing to increasing, which means that's a minimum point. Minimum. I guess spelling is not my strong suit. I'm glad I can do calculus, though. At x equals -2. And a relative maximum. Do I make the spelling challenge here? That's at x equals 6. Now, of course, if we want to know the exact y-coordinate, we plug back into the original function. Okay, so that's everything we can get from the first derivative. Now let's look at the second derivative. So f double prime of x is equal to, and this is going to answer our questions about concavity. Okay, so looking at my first derivative, now I'm going to look at the original version, because that's going to be the easiest one to take the derivative of. Again, it's a power rule. We'll say the second derivative is -6x plus 12. And again, if I want to figure out where things are transitioning, I set it equal to 0. And then I solve that for x. Subtract 12 from both sides, divide by 6. Now, what do we call this right now? It's a possible, and very likely, point of inflection. And I say very likely because we already know what the graph looks like. So here what we do is we make a sine graph of f double prime. And again, this is the analysis part of it. This is what makes it calculus, really. I'm going to plug in 3 because it's to the right of 2. But I'm going to plug in 0 because it's on the left of 2. And because it's just an easy number to plug in. So f double prime at 0 is -6 times 0 plus 12. Which is 12, which again, remember, second derivative tells you concavity. So this graph is concave up on that entire interval. And f double prime at a point on the right of 3 Now again, I don't care about the value, but I do care that it's negative. That means it's concave down. So that means we do indeed have a point of inflection at x equals 2, which oddly enough is halfway between the min and max, which is true for every cubic function. So put that feather in your cap if you ever need it again. So let's just summarize here. So if I want to locate these things on the actual curve, let's just remember everything that we got. We got our x equals 2, and that was our inflection point. We had a minimum at negative 2, and we had a maximum at 6. So f of x being negative x to the third plus, it was such a long time ago, 6x squared plus 36x plus 50. So what I'm going to do just to make the work a little bit easier is I'm going to actually put this into y equals here. And I'm going to put in negative x to the third plus, short-term memory, 6x squared plus 36x plus 50. And I'm just going to go to my table, and I'm going to delete all these out, and I'm just going to plug in the values that I want. So that would be 2, negative 2, and 6. So at 2, we're at 138. At negative 2, we're at 10. And at 6, we're at 266. So those are the points on the original graph. Now, if you look, it makes sense. If I could go back up to my original graph, I'm a little bit stuck at the moment here. But the minimum is just above the x-axis. The maximum is way above the x-axis. And the inflection point sits right in the middle of those. So I hope that gives you a nice comprehensive look at how to use all these properties for one function. We'll do another one that involves a little bit more complicated of a function, probably a rational function, just so we know that we can analyze pretty much anything that's out there. So I thank you for your time.